Hi, this is a video that is going to have three parts. The first one is going to be on just geometric proofs in general. One will be on using flowcharts to chart a proof, and one will be on doing proofs as paragraphs. All right, so we're going to start with the idea of geometric proof. Okay, so this is the idea that you're going to use deductive reasoning to move from a set of accepted statements to more conclusions using conditional if-then type statements. So the types of accepted statements that we can use. So there are certain reasons that can be used in a proof. Okay, and we generally fall into four categories. First one is given information. All right, so we know something about the situation that we're looking at, and we look at that given information. The second thing are definitions. So we have a couple of definitions already. We have things like a definition of a midpoint, a definition of an angle bisector, this kind of stuff. So we've got that. Properties or postulates. So these are things that we generally accept to be true without proof. Properties or postulates. There we go. So things like the segment addition postulate and the angle addition postulate, the ruler postulate, the protractor postulate would all fall underneath this. And finally, theorems that have been proven. Okay, so generally speaking, this is going to be where we do work to create a collection of theorems that we can use to prove other theorems. We've proven one so far. We've proven the vertical angle theorem, that if I have angle 1 here and angle 2 here, that these two angles have to be congruent. So that was a theorem that we proved. We used some of these things before. So that's one example of geometric proof that we've already seen in this course. Okay, so what I'm going to do is I'm going to prove a couple of theorems. One using a traditional two-column proof, one using flowchart proof, and one using a paragraph proof. And hopefully this will give you an idea of how to go forward. Okay, so the first theorem we're going to prove is a thing called the midpoint theorem. And this theorem basically says if you have a line segment, let's call it A, B, and M is the midpoint, right? Then the following has to be true. AM has to be half of MB. So this has to be of not MB, but rather AB. There we go. AM is half of AB. So this is half of the whole. And MB is also half of AB. That's provided that M is the midpoint as we're going along. All right, so we're actually going to try to prove this theorem. Okay, so typically when we're working with a geometric proof, the first thing that we get oftentimes is a diagram to work with. So the logical diagram here is to have a line segment AB with a point M on it and have that be the midpoint. So we have some given information. So we are given that M is the midpoint of segment AB. And what we're trying to prove, so this is the target of our proof, is that I can make a logical connection that if this is true, then AM has to be half of AB, and MB has to be also half of AB. Okay, so the way a traditional two-column proof works is that we build a set of statements, and then we give reasons for those statements. So all of our statements have to be things that we can accept because of certain reasons. So usually an easy place to start is with any given information. And we're given that M is the midpoint of segment AB. We're told that. So that is given. We're told that right off the bat, that M is the midpoint of these things. All right, so because it's the midpoint, we know that it breaks the segment into two congruent parts. So we know that AM is equal to MB. Why do we know that? Because that's what it means to be the midpoint. So why do I know this? Because the definition of a midpoint. Because that's what it means to be the midpoint. It breaks it into two equal parts. The two parts have to have the same length. AM has to be the same as MB. Okay, so this is where we're going to bring in something else. If I take AM plus MB, I should get AB. Well, yeah, the two parts add up the whole. That was something that we called the segment addition postulate. Okay, so let's see where this goes. If you look, I have an MB here. I have an MB here. I'm told that AMB is equal to AM. So I can swap out this MB and put in that AM. Okay, so let's think about what that says. AM plus AM should equal AB. All I did was I took two things that are equal and I swapped one for the other. So this is what we call substitution. This is our substitution property, right? Now, you can also word that as 2AM equals AB, right? 2AM is equal to AB. All right, so let's see where we can go from there. Aha! Well, if I divide both sides by 2, I end up with AM is 1/2 AB. That's what I'm trying to prove. That's one of the things that I'm trying to prove. What did I do? I divided both sides by something. So I used the division property. And yay, I've got one thing that I'm trying to prove. That's awesome. But I still have this other thing. But note, AM is equal to MB. AM is equal to MB. So I can just take out the AM and put in an MB. And I get that equal to 1/2 AB. That's also by substitution. Took out something that's equal and replaced it with something else that's equal. And I've proven the other half. So I've successfully proven everything that I wanted to prove. So this gives me a two-column proof for the midpoint theorem, which says that each half of the segment is half of the whole, which is not startling news, but we've actually made a logical argument based on accepted statements. It means we've got deductive logic. We can absolutely trust this theorem. All right, so that's a basic two-column geometric proof. Now that two-column format is not the only way to set up or do a proof. So I'm going to prove another theorem, but I'm going to use a totally different method. So we're going to prove something called the angle bisector theorem. Okay, so this is kind of similar to the midpoint theorem, but it's a little different because we're dealing with angles now. And this thing basically says that if I have an angle, let's call it A, B, C, and I have some ray here called BX, so that ray is the bisector, meaning that these two angle measures are the same, then I can say that the measure of angle ABX is half of the measure of angle ABC. And I can say that the measure of angle XBC is also half of the measure of angle ABC. So this is like the corresponding theorem to the midpoint theorem, but now only with angles. Now I'm going to prove this in a very different way. I'm going to use something that's called a flowchart proof. Okay, so let's take a look at that. All right, so I'm going to start off the same way. I'm going to start off with a picture. A, B, C. Oop, that one's kind of bad. Let's fix that a little bit. There we go. X, and we are given that ray BX bisects angle ABC. And we want to prove two things. We want to prove that the measure of angle ABX is half the measure of angle ABC. And we want to prove that the measure of angle XBC is half the measure of angle ABC. Okay, so I'm going to do this kind of using a flowchart picture type thing. I'm going to start with my givens. So I'm going to put a little circle here that says that's where I'm starting. And from the givens, I get a statement. Ray BX is the bisector of angle ABC. Okay, so this is a piece of information that I am given. Now, immediately from that, by the definition of a bisector, so see where I put the reason right down on that arrow? I know that the measure of angle ABX is equal to the measure of angle XBC, because that's what a bisector does. It cuts an angle into two angles that have equal measure, two congruent angles. Okay, now if I just started with the drawing, I could also draw a conclusion. Okay, and I can draw this conclusion by using the angle addition postulate. And the angle addition postulate tells me that the measure of angle ABX plus the measure of angle XBC has to equal the measure of angle ABC. Oops. So it has to be equal to the measure of angle ABC. Okay, so that's a direct statement from the angle addition postulate, that this small angle plus the other small angle has to equal the whole. Now, let's take a look. This is XBC, right? So this is like a very similar game that we used before. Over here is XBC. This is XBC. They're the same thing. I can take one of those out and put that in its place. So I'm going to use this together with this to make a statement that the measure of angle ABX plus the measure of angle ABX is equal to the measure of angle ABC. Okay, so we kind of took one statement, used another one with it using substitution, right? Two things that are equal can be substituted for each other and got this statement. Now note, a quick little bit of math here gets me that this is the same as 2 times the measure of angle ABX is equal to the measure of angle ABC, so that's just simplifying the expression. And then by the division property, I can divide both sides by 2 and get that the measure of angle ABX is equal to 1/2 the measure of angle ABC. And in the end, that's a statement. And that is one of the two things that I'm trying to prove. That's this guy. I've just proven it. Okay, so I've used this row with this row, and I've got it there. Now, let's do a quick little think here. ABX, according to this, is the same as XBC. They have the same measure. So I'm going to use this. I'm going to use this together. Again with substitution. And I can now say that the measure of angle, not ABX, but XBC, is half of the measure of angle ABC. And that there is the other thing I'm trying to prove, that XBC is half the measure of angle ABC. So I have proven both of these things. Now, this looks completely different than my two-column proof. Okay, the statements are the things in the boxes. The reasons are things along the arrows. But yet, this actually shows a much more clear connection that these two things worked together to get this one. These two things work together to get this one. So sometimes this is a little bit more informative. It looks a little less formal, can be a little bit more messy, but the entire thing is maybe a little bit more informative. Now, we've got a third type of proving things here that we're going to call a paragraph proof. And I'm not going to prove an actual named theorem here. I'm just going to kind of build something from a drawing. So let's say that we have a drawing, right? And this drawing has a segment AB, and it has some other segment CD. And we know a few things. We know that AB is the same length as CD, and that if I take the midpoint of this segment, right, so M is the midpoint of this one, and N is the midpoint of this one, right, we want to prove that ultimately that MB, so we want to prove that MB is the same length as ND. Okay, so I'm going to do a little flipping back and forth between the notes that go with this video and kind of this sketch that I just made here, and show you how this plays out. Okay, so I'm looking at what we would call a paragraph proof here. Okay, so that's what's given kind of in this section right here. Okay, and if you take a look at that, it's actually explaining step by step what the proof would say. So it says, given that M is the midpoint of AB. Okay, so if I flip back to my drawing, it's really clear there that M was given as the midpoint of AB. Okay, so we know by the midpoint theorem that MB is half of AB. So MB here is half of the whole thing. Okay, so that makes sense. Now likewise, given that N is the midpoint of CD, so go back to my drawing, N is the midpoint of CD. Okay, I think you can see where this is going. Also, by the midpoint theorem, ND is half of CD. ND is half of CD. So MB was half of AB, ND is half of CD. So MB is half of AB, ND is half of CD, but since AB is equal to CD, that was in our givens. AB had to be equal to CD. Okay, so since that is true, since we were given that, we can use the substitution property. Okay, so wait a minute, these two things are equal. So I can take one out and I can put the other one in. So what I did here is I took out the CD, and I took out the CD, and what am I going to put in there? AB. So now ND is half of AB. Okay, so now I've got a situation where ND is half of AB, MB is half of AB. These two things are both half of AB, which means they have to be equal, right? That's by the substitution property. If they're both equal to the same thing, they're equal to each other. You can take this out, you can swap the ND and put it in there. All right, so we can say that MB is equal to ND, which, lo and behold, was what we're trying to prove. Woohoo! We got it. Okay, so the advantage of the paragraph proof is that it uses just like the customary English that we're used to, and that's where we play for this. Okay. All right, so there we go. We have seen 3 types of proofs today. We've seen a standard 2-column geometric proof. We have seen a flowchart proof, which is a little messier, but it definitely gives us more of an idea of how the ideas flow. And finally, a paragraph proof. We'll use all of these in class, but generally speaking, the one we're going to lean on the most is a 2-column proof. And that's it. They all use previously accepted statements in order to draw new conclusions. And that's where we're going to go from here. Thank you.